So, we will continue our discussion now with the discussion of the uniqueness theorem in electromagnetics. Okay. So, before we go into the details of the uniqueness theorem, there is a very practical reason why we should be interested in something which says uniqueness, and that is this. Supposing I take a practical situation, let us say there is an antenna in this, mounted on this room that is radiating fields everywhere, and you as someone who has taken this course on CEM is asked to calculate what are the fields. Now, you do it, and if the answer is not going to be unique, then what is the point of doing the calculation, right? So, thankfully for us, there is a very powerful theorem in electromagnetics which guarantees us that under certain conditions the answer that we get after our laborious calculations will be unique. Okay, so that makes it whole worthwhile. Okay. So, the statement of the theorem is as follows. Okay, so it says that the field, and by field I am talking about E and H, created by some sources J. Okay, so let us take some volume over here and let us put some current source over here J. Okay, and this is going to produce a field E comma H. So, what is the theorem saying? That if I take a source J inside a lossy volume V, then the fields are unique under any of these three conditions. Okay, it is not all, it is any of these three conditions. So, what are these three conditions? So, this volume has some surface S. This is saying that E tangential over this surface. Supposing I know E tangential over all of S. Okay, if that is specified, then whatever you get as the result of your calculation, the fields, they are unique. There is no other solution that is correct. Okay. The next condition is analogous, because we have seen that there is a sort of symmetry between E and H fields. So, it says okay, if you do not know E tan, if you know H tan over all of S, then the field is unique. And then there is of course the third option is a sort of a linear combination, that you give me E tangential over some part and H tangential over the remaining part. Okay. So, under these conditions, any of these conditions, the field that you will get is unique. Okay. So, this also tells you that if you were to approach a CEM problem, you need to specify the tangential E fields on the boundary. Once you do that, you are guaranteed that whatever procedure you use for solving these equations will give you a unique solution. Okay. Now, you might ask, supposing I put an antenna like this over here and it is in free space, absolutely nothing anywhere. So, in this case, will the fields be unique? There is no boundary anywhere, it is in middle of interstellar space. Will the fields that you get from this antenna, supposing I have specified the current over here, will they be unique? Answer is yes, because the boundary is at infinity, and because this is a physical field, it cannot go on forever. So, trivially the E tan and H tan is 0, right. So, in this case I have specified E tan and H tan implicitly without even thinking about it at infinity to be 0. So, in this case the fields are going to be unique. Okay. So, sort of elaborating a little bit more on this example, this was an example of a closed volume. Okay. You may come across another different kind of volume which is like this. Let us say this is, let us say, volume V naught, and there is a current source over here J, and this is volume V. Okay. And there is no boundary over here, this boundary is infinity, and I am talking about region V. So, now what do I have to specify for the fields to be unique? On which surface? So, this is S infinity and this is S. So, this theorem holds true here also, whatever surfaces are bounding the volume. So, for this volume V, what are the surfaces? S infinity is one surface and S is the other surface. S infinity being infinitely far away, fields are physically, they will go to 0. So, I know the tangential fields at infinity. I need to tell you what the fields are, the tangential fields are on this boundary, and then once these are specified, I know that I can proceed with my calculation, because my answer will come out to be unique. So, a very simple example of this is if for example, this volume V naught is a solid perfect metal. So, perfect metal will have tangential E field is 0, right. So, once I have such a situation, I know that the fields in this volume V will be unique. Okay, that is just a simple example. All right. So, is this uniqueness theorem clear? Now, you might ask why this lossy volume V, right? Why should the volume be lossy? What if there was no loss in this medium? So, the answer to that is not clear just from the statement of the theorem. We will have a small exercise in a homework problem where you can work it out. When you take Maxwell's equations and solve them over some volume, you will find that you need to specify some tiny amount of loss for this theorem to hold true. Practically, this loss can be really small, so that you can effectively treat it like a lossless volume. Okay? Even though we say free space is lossless, right, even air we say it's lossless, but actually there might be some really tiny amount of loss in it which allows this theorem to be applicable. Okay? Question?
So, can we say when the field is not unique, can we set example?
So, if these conditions are not satisfied, then we cannot make any statement about the uniqueness of the theorem of the fields. That is all there is. Okay, so, you may be able to construct examples where you have not specified E tan or H tan over the entire boundary. In that case, you may get many solutions which satisfy the partial information which you have given. That is possible. Yeah.
Why doesn't the theorem talk about
Charge
charge density?
density, so we are in this particular case, we are dealing with a case where we are talking only about currents. Okay, so we are talking about electrodynamics, not electrostatics cases. Okay, yeah. But the theorem could be extended also in that case.
No, static charge doesn't.
Yeah, in this we will not deal with static charge. In fact, if you Griffiths has a very nice discussion about it. A static charge is not going to sit there; it will fly off somewhere or the other, unless it's in a place where there is no fields whatsoever sitting there forever. So, we practically speaking, when you think of antennas, radar cross sections of antennas and all, the issue of charges sitting out there is not very relevant. Okay, all of those charges, once they start moving, they become currents, and we are already dealing with currents. Okay. So, this was about the uniqueness theorem.